Hello, I am Mohd Asif Ansari, currently in my second year, third semester of the Masters in Construction Engineering and Management program at CEPT University. The work I am presenting today is a part of my Studio 3 titled Implementation of Integrated Construction Practices Approach to Construction Projects with the case application on the Iconic Curve project. This project allowed me to explore BIM-based coordination, lean methodologies, 4D and 5D planning, stakeholder alignment, and real-time digital workflows, providing a practical demonstration of how modern integrated practices can significantly improve construction efficiency, risk mitigation, and decision-making across a complex commercial high-rise project. Now moving on to the project brief. The Iconic Curve is a greenfield commercial real estate project in Gift City, built on a 4,316 square meter plot with a 2,637 square meter built-up area, having 441 offices plus 12 shops. Designed with a 38-degree twist, it targets an iconic landmark identity through unconventional and structurally innovative design. The project follows a square feet rate contract and is planned from 2023 to 2029, valued at rupees 397 crores. Our scope focuses on the ground floor and basement one floor, where we implemented integrated construction practices approach to understand its impact towards seamless project delivery and efficient construction. Moving on to 5D simulation using Naviswork. For the Iconic Curve, we conducted an integrated 5D simulation in Naviswork by connecting the LOD 400 basement and ground floor models with the project's baseline schedule and resource data. The workflow covered importing the 3D model, linking scheduled tasks, assigning scheduled resources, and generating cost and simulations. We put resources in a manner that in case of a core wall, reinforcement costed 13 lakhs 9,000 rupees. Manpower deployed for the same costed 1,65,200 rupees and machinery involved for the same costed rupees 55,658. While the planned timeline was 16th April 2025 to 31st July 2025, actually the work started on 17th October 2025 and our status date to check the progress was 18th November 2025. The simulation revealed delays and showed that altering the core wall sequence disrupted dependent activities like beams, slabs, and staircase, supporting how impactful 5D simulation will be for planning and execution decisions. Now moving on to 5D simulation use and earned value management. For the Iconic Curve, we perform earned value management to evaluate project performance for basement 1 and ground floor. Using LOD 400 models, we created the WBS defined calendars, assigned baselines, and leveled resources. The planned value was rupees 13.43 crore, while the earned value reached to rupees 1.97 crore. However, the actual cost rose to rupees 1.98 crore, resulting in a cost variance of negative rupees 59,209 and a schedule variance of negative 11.45 crore rupees. With cost performance index at 0.997, the project is slightly over budget, and an schedule performance index of 0.147 indicates only 14% progress of the planned rate, showing significant schedule delays. As there is no inbuilt technique for earned value management in the Naviswork, we perform the earned value management using Microsoft projects. Moving on to implementation of last planner system in construction phase. For the Iconic Curve, we implemented the last planner system during the construction phase to enhance planning reliability for basement 1 and ground floor. Using milestone planning, phaseful planning, a 3-week look ahead, and weekly work plans, we monitored planned versus actual progress. In week 1, out of 12 planned activities, only 7 were completed, giving a weekly percent plan complete of 58%. Delays occurred due to inadequate manpower during the Diwali period and congestion in core wall reinforcement which affected constructability. This congestion in core wall reinforcement delayed the dependent activities which were shuttering and concrete of the core wall, which eventually resulted in delayed activities such as the slab reinforcement, shuttering, and concrete. The last planner system helped us map constraints in real time and guided us corrective actions to improve workflow reliability. Now moving on to track the look ahead plan that we prepared during the last planner system using percent plan complete. For the Iconic Curve, we tracked constraints across 3 weeks of last planner system implementation from 27th October 2025 to 15th November 2025. Planned tasks increased from 12 to 24, but actual completions remained low as 7, 8, and 9, resulting in percent planning complete values of 58%, 40%, and 38%. Constraint analysis showed dependency issues as the highest contributor with 21 occurrences, which is 62% of the total occurrences of the constraints, followed by inadequate manpower at 11 occurrences and constructability issues at 2 occurrences. Week 1 delays stemmed from manpower shortage post-Diwali. Week 2 faced continued delays in Port 4 due to the same reason, manpower shortage post-Diwali, and Week 3 saw reinforcement congestion in core wall, slowing slab and staircase works. These insights strengthen our understanding of how large panel system will help in corrective planning and improving workflow reliability. Now moving on to integrated construction practices approach risk mapping. For the iconic curve, we analyzed BIM related risk across planning, design, technology and management, operations, finance, process, human resources and quality using a probability impact matrix. Severe impact likely risk included unclear EIR P1, model conflicts D3, schedule misalignment PR1, incomplete as-built models O1 and skilled staff shortage HR1. Design risks recorded the highest count with 7 occurrences, followed by planning and operational risks. Major impact likely risks such as lack of training M3, outdated site models O2 highlighted operational inefficiencies. Severe impact possible risks like data inoperability issues D1 and poorly executed BIM plans M2 showed that even infrequent errors can critically affect BIM reliability. Now moving on to integrated construction practices approach risk responses. For the iconic curve, we assessed ICP approach risks that commonly arise during BIM implementation. Key risks included poorly executed BIM execution plans, corrupted files, or common data environment downtime, data breaches, unclear model ownership, software errors, interdiscipline clash conflicts, delayed RFIs, weak collaboration, and cost overruns from poor 5D integration. To mitigate these, we adopted ISO 19650 templates, cloud backup schedules, access protocols, defined ownership clauses, regular software updates, weekly clash detection, centralized RFI tracking, video-based coordination, and live cost databases. The inferences indicates that while ICP adoption carries multiple vulnerabilities, structured response strategies can significantly streamline BIM workflows and reduce project uncertainties. Now moving on to the benefits of ICP approach over traditional approach towards project. For the iconic curve, we compared the traditional construction workflow with the ICP approach using BIM-based collaboration. Traditionally, communication is fragmented through drawings and emails, causing interpretation issues, late clash discovery, and RFI delays. Under ICP, a common data environment integrated model provides a single source repository with live updates, while 3D and Naviswork enable early clash detection during design, reducing rework and delays. ICP further enhances real-time collaboration through ACCE, improves site logistics with Revit, and ensures timely execution using the last planner system. The pool-based planning improves reliability during execution. Overall, ICP drives faster coordination, early risk detection, and improved schedule reliability through proactive planning. Now moving on to real-time visualization of project to site team through Dalux software. For the iconic curve, we use Dalux for real-time BIM visualization by exporting coordinated architectural, structural, and BPF models from Revit and uploading them to the platform. Dalux allowed seamless model federation and enabled site teams to access the latest model updates both on desktop and mobile. This significantly improved spatial understanding, clash visibility, and installation clarity. Site engineers could visualize service routing directly in the field, eliminating interpretation errors from the drawings. An important inference is that only the master source models are editable, ensuring data integrity and preventing unauthorized modifications. Dalux provides an always updated, clash-free, and highly accessible digital model for decision making. Now moving on to the conclusion. For the iconic curve, we map challenges using Lean's downtime-based framework across initiation, design, and construction phases. Key issues included poor design visualization, manual quantity takeoff, delayed RFIs, lack of contractor involvement in the project in the early stages, fragmented communication between the stakeholders, no common data environment, site level inefficiencies, and poor procurement planning integration. Using ICP methods such as BIM coordination, Dalux mobile visualization, 5D integration, large planner system implementation, and common data environment workflows, many issues highlighted were successfully eliminated, reducing rework, increasing visual clarity, enabling real-time updates, improving project sequencing, and enhancing cost monitoring. This demonstrates measurable value creation by eliminating waste through integrated practices.